Okay, this is Mr. Anderson from Kellogg Community College, using some new software and hardware today, so bear with me a little bit as I fumble through some of the menus and navigation panels that you're not seeing on the screen, but I'm kind of dealing with in my toolbar here. So what we're dealing with today is the central limit theorem. The central limit theorem looks at a small group of a large population and evaluates the percentage of an average happening, or it looks at the chances of something in that small group of coming true. And that's very useful, especially taking a look at the first part of this problem here. It says, on the average, a U.S. couple will spend $26,542 for their wedding. However, the majority of couples spend between $19,907 and $33,178. This does not include the cost for a honeymoon nor the engagement ring. Understanding wedding costs can help you with your wedding budget later. Now, this is coming from a website called thecostofwedding.com, and I took this from February 20th of 2012. Now, what's cool about this is that they tell you that the average is $26,542. So that is going to be our average of mu. So mu is equal to the $26,542. And our standard deviation is also given in this problem because they said that most people spend between $19,000 and $33,000. And by doing a little subtraction and addition, you can see that they gotten a number of $6,636. So the standard deviation is $6,636 from this population. But we're really interested in looking maybe at a smaller sample size, because maybe as a florist or a someone who works with weddings, catering, or if you're going to be the manager of the wedding, you're going to want to know maybe in your group of 30 people that you can see during the course of a year for maybe 30 out of 52 weeks, you're going to be interested in what is that small subgroup's likelihood that that average will be around that amount. So the main reason that we are interested in these kind of smaller samples is because, in business and also maybe in your scientific study, your region or area might have a different spread, and that spread right there is going to be a different size than your actual total population. See, we're going to be dealing with something called the distribution of sample averages. Because when we look at a sample group, their averages may not exactly match the actual average of the entire population. But if you take enough samples, then you will actually get the same average. But that smaller group is a distribution. This is a distribution using the averages from all possible random samples of a specific size. Now, you are going to get some sampling error. The sampling error is going to occur because your smaller group is not a perfect representation of the larger group. So the sampling error is the difference between the sample and the population due to the fact that the sample is not a perfect representation of the entire population, because you're looking at a small group, hopefully 30 or more, but sometimes not even that much. But 30 or more is really what the book and we target. So we're going to now take a look. Sorry, I went down too far there. We're going to look at two properties of our small sample. Our small sample has to have the same mean as the entire distribution. And also, the sample's standard deviation will be smaller than the population. So to show that to you here, if our normal curve on a straight line looks like this, if we take a sample, or our distribution of a sample average, if we take that, it's going to have a smaller standard deviation, which is going to make our graph look skinnier, even though the average will be the same. The distribution won't be as varied. But as we get bigger and bigger sample sizes, what will happen is that this will get closer and closer to the total population. So when our sample size is very small, we're going to have a very small standard deviation. But as our sample size gets bigger, then we're going to have a much bigger standard deviation to where it's actually going to match the real mean and standard deviation of the entire population. And this is why we're going to bring up the central limit theorem. Looks like I crossed that out, but I was trying to underline it. The central limit theorem, I did it again. The central limit theorem is going to take a look as we increase our sample size to get as close as we can to the actual population. Now, let me give you the central limit theorem and its definition here. I've typed it again, but I'll show it to you as I say it. As the sample size grows, so we want bigger and bigger small parts of our entire population. As the sample size grows, the shape of the distribution of sample averages, or sample means as the book says, chosen with replacement, with mean of mu and standard deviation will look more and more normal. So what that means is that if we take our small sample group, and that small sample group has all their sample averages, and we can choose them with replacement. That means if I choose 30 people at random, there's a possibility somebody could get chosen twice. With an average and standard deviation, as it grows and grows and grows without stopping, without bounds, you're going to get it to look like the actual standard deviation. And it has a formula. The formula for that is going to be very much like our old formula for standard deviation. Our formula is going to look like this. To find our z-score, instead of using the entire population, we're going to use a small target group, which their average will be, that target average will be x bar, and we're going to subtract that from our average and divide it by, instead of dividing it by the standard deviation, we're going to take our standard deviation and divide that by the square root of our sample size. Now this denominator here is the standard error of the mean. The formula, which is the standard deviation divided by the square root of our sample size, is proved on page 331 and 333 on the book. You can see where they take a look at all the different sample sizes of a certain population, in this case a population that goes between 2 and 8, graph it out, and then show you that the square root of the sample size, dividing it from the standard deviation, will give us our standard error. And that is very important because when we deal with a smaller group, we can't just use our normal z-score formula, which is our target score minus the average divided by standard deviation. We have to modify that denominator, and modifying that denominator will take into account the error of our small subgroup. And what will happen is that the larger our group gets, 30, 40, 50, 60, 70 people, or thousands of people, you'll see that what will happen is that this number will get closer and closer to our actual standard deviation, because this number is going to get exceedingly small, and so this division will make less and less of an impact. All right, so let's go and start to apply this formula. Okay, so applying the formula here, I'm going to write this down at the top of the screen again so we can use it for our first part 1 of the problem. All right, so the formula is, our formula is going to be our target average subtracted from the average of the entire population divided by the square root, sorry about that, the standard deviation divided by the square root of n. Alright, so here's our example. Children between the ages of 2 and 5 watch an average of 25 hours of television a week with a standard deviation of 3. If 20 children, and that's going to be our sample size there, lower than what we want because we're really wanting 30 or more, if 20 children were randomly selected, find the probability that the average number of hours TV would be greater than 27, below 24, and be between 23.5 and 26.5. So this is going to be a 3-part question. The first part is we're going to find out what is the standard deviation, what are the chances that our small group of 20 students will have an average greater than 27 hours of television. So what we're going to do is make our normal curve, but notice this normal curve is not going to be as like the normal because the standard deviation is smaller. Our average, our mu, was 25, and we got that from the problem up here. This is our mu, or population average. And our standard deviation was 3, so we're trying to find out what are the chances that our population was above 27 hours. So we're looking for that area above here. So again, our formula written up there, we're going to plug it in for my z-score to try to figure out that percentage of that happening. So our target was 27. That's our target score right there. That is our x-bar. Subtract our mu, and the mu is going to be our average there. So that's going to be 25 divided by, in parentheses here, we're going to have the standard deviation, in this case 3, divided by the square root of, in this case, 20, because that's our sample size. Again, a little on the small side. So what we're going to have here is the numerator is 2, and our denominator is, if you turn on your calculator and go 3 divided by square root of 20, it rounds to 671 thousandths. And 2, I know that looks like a z, but 2 divided by 671 thousandths is going to be almost 3 standard deviations away from this small sampled norm. Now if we go to the table in your book, it's in the front cover or on page in the 700s, we can find that the z-score of 2.98 is approximately 99%, close to 100%. So that is going to be 99% are below that 27. So to find out how much, in the context of the problem, how many were greater than 27, we're going to go 1 minus 0.9986, which is 9,986 ten-thousandths, and we get a decimal of 0.0014, which is 14 ten-thousandths, so that's approximately 14 hundredths of a percent. So not very likely. It's not very likely that we'll pick 20 students at random and have their average being above 27 hours of television. 27 hours of television that week. Now let's do the next problem. We're going to try to see what are the odds that what's the probability that there will be less than 24 hours as their average. So again, we're going to make another small distribution right there. Our average is still 25, and we want to see if we pick a group, what's the percentage chance that group will have an average of less than 24 hours. So in this case, our target mean score is 24 minus our average, which is 25, and we're going to divide that by, in parentheses again, our standard deviation divided by the square root of our sample size. So our numerator here is going to be -1. Our denominator here is going to be 0.671, or 671 thousandths. And that gives us an answer of, when we do the division, -1 and 49 hundredths. From the table in the front of the book, or in the 700s, that table B for our normal distribution, we'll make sure that's, yep, oops, sorry, not table B, table E, is going to say that our z-score of -1.49 is going to have a percentage of about 681 over 10,000, or about 7%, 681 hundredths. So our z-score being -1.49 gives us a percentage of about 6.81%. So that your likelihood of picking 20 students and getting an average of less than 24 hours, well, it's not very likely. It's only about 7%, which means that we're probably going to be, with a small group, having an average that's close to 25. So, let's continue to the next piece here. Let's pick part 3. We're looking between 2 marks. So we actually need 2 different z-scores. So what I'm going to do is do my z for my 26.5 first. That's our target average, divided by, again, this is 3 divided by square root of 20. And I'd put that in parentheses on your calculator, so that way it doesn't make a mistake. And we're going to go 23.5 minus 25 over 3 divided by square root of 20. Alright, you may want to pause the video and go and check this out and try to get the answers. Now you've unpaused it, and let's go take a look. We got 1.5 divided by 0.671, and we got -1.5 divided by 0.671. So 671 thousandths have been in the denominator each time because we haven't changed, the standard deviation won't change and our sample size is not changing. Looking at our answer on the calculator, we get 2.23, 2 and 23 hundredths, and -2.23. And that would make sense since we're really looking at a symmetrical standard deviation. Take that down to the bottom there. This is 25, and we're trying to see what percentage of the population, if I pick 20 students at random, is going to be between 23.5 hours of television and 26.5 hours of television. And this is going to be pretty high because we're not including the middle set of this curve, but we're including a lot on either side. So if I go to my table, table E in the cover of the book, this is 0.98%, or 98%, almost 99%, and this is going to be, on the lower end, only about 1%. But when we're finding the distance, when we're finding that measure between these two zones, we're looking at the difference between the two of these. Remembering that from the previous section, the area between two regions is the subtraction of the highest minus the lowest part, which is going to give me the population, or the chances that this will occur, is about 97.42%. So it's very likely that if I pick 20 students, or 20 little students between the ages of 2 and 5, the chances that they would have watched their average would be between 23.5 and 26.5 hours is very likely 97.42%. Now our final part of this lesson today is to take a look at people getting confused about when to use the central limit formula and when to use the z-score formula. Now, this means the better memory you have, the easier it is to get these two confused. So what we'll do here is we're going to show you the central limit formula, which we've just applied, which is x bar minus the average divided by the quotient of the standard deviation and the square root of our sample size. Now remember that the z-square formula is when we have, whoops, sorry, that shouldn't be there. Tough to erase here. The target value subtracted, or actually minus the average divided by the standard deviation. So you get to wonder, like, oh my gosh, when do I use this formula? And when do I use this formula? You're going to use this formula when you're going to get info on a sample mean. And again, getting used to my new hardware here, so forgive my poor penmanship, which isn't actually too much better than my normal penmanship. We are also going to use this when you want to find an individual data point. So here's an example. And you'll see when we use the central limit formula versus using just a normal z-score formula. A person consumes on average 218 pounds of meat per year. The standard deviation is about 25 pounds. We're going to find a probability that a random person will eat fewer than 225 pounds annually. And then we're going to find, if a sample of 40 people, what is the chances that the average would be below the same amount. So here's what I'm going to do. I'm going to scroll up a little bit here so you can see when we use each formula. For part A, what we're going to do is we're looking at a random person. So a person will eat fewer than 225 pounds annually. So the chances of that happening, we have to look at the entire population. And the entire population has a normal curve. Its average is 225. Oh, sorry, its average is 218. Sorry about that. So the average is 218. And we're going to have 225 be that target for that person. So what is the chances that a random person will be below that 225 right there? So we're looking at that. And this will require us to use our normal z-score formula because we're looking at an individual person and their difference from their average divided by the standard deviation to find our z-score. And that gives us an answer of 7 over 25, which is 28 hundredths. From the table, E, which is on the inside cover of your book, 28 hundredths is at 61%. So approximately 61% of the population will be below 225 pounds of red meat eaten per year. But now, that's the first part of the problem. The first part of the problem was asking about one person. Now the second part of the problem is asking, if you pick 40 people, find the probability that the average would be below 225 pounds. Well, when you pick a small group, your chances of getting a vegetarian are going to be much smaller. So even though this is a little skewed, I didn't mean to make it that way, it's still going to have the same average of 218. But our group size is so much smaller, so our standard deviation is so much smaller. So in our group of 40 people, our numerator still looks the same, 225 minus 218, compared to our normal z-score form or z-score formula. But our denominator, instead of dividing by 25, we're going to divide it by that 25 divided by our square root of our sample group, the square root of 40. So that means 7 is going to be divided by a much smaller number than 25. So this is going to be 3.953. And that gives us 1.77, which is much further away than our 0.28. So 1.77 is equal to about 96%. So that means that in a small group of 40 people, very small group, we're going to have roughly 96% of the population is going to be less than 225. Now you might be going like, wow, how did 96% of the population get in this picture where this up here in this picture is only 61%? Well, this middle section has so much more inside of it because it's all scrunched up inside of this smaller distribution. You see that your chances of picking a lot of meat eaters in a small group is actually much more likely than picking one person out of a giant big group. All right, to end the worksheet here, we're going to go to the very bottom of here, and we're going to take a look at this question. We're going back to the wedding problem. We're having an average U.S. couples spend this much for their wedding, so this is going to be my average, and this is going to be my standard deviation. Find the probability that a random person will spend less than $15,000. All right, well, since we're looking at a random person, we're looking at $15,000 minus our average, 26,542, and we'll divide that by our standard deviation of 6,636. So that's for our first part of the problem. Find the probability that a random person will spend less than that. Now, without doing the problem ahead, let's just look at the second part here. Find the possibility that a sample of 30 people, it's kind of what we want 30 people, will spend above $25,000. All right, so we're looking at above 25 grand, so here's our 25,000 minus our 26,542. And then we will divide that by our 6,636 divided by the square root of 40. Now this would be a good place to pause the video and try to see where you are, where you are in that mix right there. Pause the video and do the work, and now here's going to be our answer for each of these. Doing this, the numerator is going to be negative 11,542. Try to make that look like a comma. And the denominator is going to be 6,636. We do the division and we get an answer of a z-score of negative 1.74 or 74 hundredths, which means that we're going to have a percentage of about 4%. So it's not very likely if we take the entire population and we pick somebody at random and their wedding's going to be less than 15 grand. It's 4%. Not very likely. Now, what we're going to do is try to take a sample of 30 people and see what is the chances that they will have an average more than $25,000. All right, so here we have that target score there, minus 26,542. If we do this, our answer is going to be negative 1.27. I did skip the step here. I computed this and did my division down there. And whoops, I put a 40 there. I really should have a 30 there. So let's make that a 3 instead of a 4. Sorry about that little writing typo there. And I'll find out that that is going to be on my standard deviation chart about 10%. But remember that on the standard deviation chart, it always talks about below that amount. So if we want to find out what's the chances people will spend above this amount, we have to subtract that score from the 10%, and that makes a total of 90%, or 0.9, or 8, excuse me, 0.89. Wow, that's a funny looking 8. That's 898 thousandths, or about 90%. So it's very likely that if I pick 30 people at random, that they're going to be spending more than $25,000 on average. So that looks good for my business model. If I'm going to be a wedding manager, if I'm going to be a consultant, or if I'm going to be a florist, or maybe even a DJ, I'm going to want to know these figures. So go ahead and do these two pages and those odd numbered problems. Use the solution manuals to help you out, or give me an email if you have any questions. And that was my first go with my new software and hardware. Thanks for putting up with me, and as future videos will be a lot more smooth than this one.